afterwards. Yeah, my name is Torsten Hoefler. I'm a professor at ETH Zurich, and today I'm here to give actually a quite complimentary view to DK's wonderful talk. So DK told us about all the practice in high-performance computing in MPI and personalized MPI libraries. I'm really looking forward to have this at some point. And now I'm trying to give you a little bit of the basics. What is behind it? So what are the concepts behind MPI? What are the new concepts? And especially, how do we go to the next generation of network interfaces that we then employ in maybe 15 years or maybe 10 years MPI to come. But let me first start from the past. So what happened in the past and how are we going forward based on this into the future? I mean, we all remember the good old Ethernet that we have been using in high-performance computing actually at the very beginning, but that was quickly replaced by something with a scalable coherent interconnect. But then we realized that actually large-scale cache coherence is not the most performant way of doing things because it requires an n-square overhead. So scalable and coherent in a single name is actually not a very good idea, but it seemed so in the 90s. That was quickly replaced by active message-based communication in the fast message library. We all know Myrinet, more or less rest in peace. It still exists in pieces, but that was the first one that introduced operating system bypass. So it revolutionized actually networking in many different ways, and then it moved ahead into this area of protocol offloading. Quadrix, the other company, rest in peace. So DK just told us about it, that they were the first to offload collectives and things like this. Yes, unfortunately, the business case wasn't too strong. And then VIA introduced the zero-copy architecture that we've just heard about, was adopted by CryGemini. InfiniBand then termed the coin remote direct memory access, which is what formed much of the basis of much of our work, including DK's and my work for the past couple of years. OFET replaced this as an interface, basically. And then we had Portals 4, which is a quite interesting interconnection specification. There are some NICs out there, but they are not widespread. But they add a new functionality that's going post-RDMA. These are so-called triggered operations. So these are for the first ones that kind of give us a bit of a more programmable network interface. So it's a very limited interface, but it's quite powerful. And then libfabrics took up many of the ideas of portals and standardize them further in a wider availability. So today I'm going to focus mostly on the first part of the talk on RDMA, remote direct memory access, because it is one of the more important interfaces that we've been looking at in the previous years. So as we can see down here, actually most of the top 500 systems are using RDMA as an interconnect, and we just heard about all the goodness of the technology itself. So in fact, there's one thing that we should know. RDMA is not so easy to program. There's actually a semantic mismatch between the semantics that RDMA gives us and the MPI interface. MPI is a messaging interface. It sends messages from A to B. RDMA is an interface where I write data at B from A. It's fundamentally different from sending messages. So it's quite hard to implement this in practice, to implement an optimized MPI, to use RDMA facilities. And much of DK's work, we really aimed at this. So trying to bridge the semantic disconnection between the two. The MPI forum has a slightly different approach, where we basically just said a while ago that we need to support the RDMA facilities more natively. So we need to somehow specify or extend the specification with a way to program RDMA directly. So in this sense, MPI, the message passing interface, is not just message passing. It actually has a quite large part that I would call PGAS. So I mean, actually, MPI one-sided existed before PGAS, so we can argue what the right naming should be, but somehow PGAS is much more popular as a name because indeed it is a partitioned global address space. And this is MPI 3. In MPI, as I mentioned, it's called RMA or MPI one-sided, so either remote memory access or just one-sided accesses. It has little to do with messaging, in fact. So I want to give in the first, like say, 15 minutes, a quick tutorial on how this in fact works in practice on the fundamental basis. This is supported on all major supercomputers that support RDMA. It's also in MVAPIC. It's in basically every MPI implementation. Speeds are varying, as we will see in a couple of minutes. So this was just one of our papers how to implement this. This appeared in the 2018 ACM research highlights, or communication of the ACM as a research highlight. So this is why it's highly highly well, timely in this sense. So, but let me give you this overview of what MPI RMA really is. So as I mentioned, it's supported by the MPI 3 specification, which has been out for a while, but implementations still take a while to take this up. And the most important feature here is that communication is really one-sided. And one-sided means there is no involvement of the destination. It's purely one-sided. And of course, the one side that is involved is the origin of the operation. Right? So if I want to send something to you, I'm not asking you. I just write data into your memory, and then I may be telling you later. But there is actually no involvement of you in this communication, which really means, at the fundamental basis, that RMA decouples communication and synchronization, which is very different from message passing. So if you look at this two-sided, which is basically message passing below, we see that the communication is actually coupled with the synchronization. What does that mean? If I'm sending the message cannot be received before the receiver says he or she wants to receive the message. Right? This is what MPI receive means. I'm ready to receive a message. I will not receive a message in message passing if I haven't posted a receive. Right? It's quite trivial. On the other hand, in one-sided, I may receive a message, or I may have my memory updated without me asking for it. Right? That's a huge difference. And the synchronization is really at the source here at process A, which then explicitly synchronizes. So it decouples communication from synchronization. Quite an important concept. So let me now give you a bit of an overview of the talk. So I'm going to talk about these fundamental concepts, then how we create windows, then how we communicate, we synchronize, and then I give you some numbers at the application so that you believe me that this is a useful concept, that it also scales and works in practice. And then at the end, actually, it's not the end, it's more like the half of the talk, I'm going to talk about what comes next. Because all I'm talking about in the first 20 minutes, as I mentioned, already exists. We can use it today, but the question is academically seen, where are we going? And we are going into a very interesting area of accelerated NICs. We see the first pieces today, accelerated networks, as we will have in the next talk, which is on Mellanox's SHARP, which is one step into this direction. But I want to line out a more global roadmap towards this. So thank you for placing my talk perfectly between DK and the SHARP talk. So, and then I will give an outlook of what's happening next in this field. So first, to introduce a bit more on MPI RMA, how does this work? Well, here we have a couple of processes, process A, process B, C, and D. They all have different address spaces, and that's now the key, because in MPI RMA we access remote memory, so we access addresses at the remote host. What does this mean? Well, first, what's quite important in MPI, we have to expose that memory to remote processes. So here we create a so-called MPI window, and that is the only memory that can be accessed remotely. Right? So we consciously, I as a process consciously decide what memory do I want to make remotely accessible. This is very different from OpenMP, for example. In OpenMP, by default, my whole heap is remotely, to other threads on the node, accessible. So you could also use this as a more structured programming model for shared memory programming, because it works on the same node. We heard about XPMEM. The same implementation can be used, or the same principle can be used for very fast on-node MPI communication through this interface. Okay, so then we have multiple different calls. We have a write call, which is called put in MPI, where we write remote memory. We have a get call, which is called get in MPI, but it's really reading remote memory. So put is write, get is read. And then we have atomic operations, which are obvious, like atomic operations, compare and swap, fetch and add, and all of these operations that you may need for atomic updates at the destination. They have some semantic specialties, but I will not have time to talk about those. In case you're interested in all the details, the 15-minute overview I'm giving you here is easily expanded to a 4-hour lecture that we give at ICS in the Advanced MPI tutorial. In case you really want to know how it works in details, this is again just a quick overview over the concepts here. So the synchronization mode is actually quite interesting in MPI, because we heard that it's not cache coherent. So we need to explicitly make the memory coherent, which means that the programmer needs to do something. What does the programmer do? The programmer synchronizes. After the programmer has issued puts and gets, nothing is happening in the network until, at least on the logical basis, until there is some synchronization. So MPI 3 gives us 3 synchronization modes, which is the active target mode, which you would use for all kinds of quite large-scale synchronization when you want to synchronize everybody. Then there is a post-start complete wait mode, which is a bit more complicated. I won't have time to talk about this, but this is really if you only have want to synchronize with a limited number of neighbors. Then there's a passive target mode, which I would heavily recommend not to use at all. It's there for historic reasons because it used to be an MPI 2. And then there is the new MPI 3 synchronization mode, lock all, which is the mode that is basically equivalent to OpenMP programming. So if you know OpenMP flush, the directive, so who knows OpenMP flush? Who has heard about this before? Not so many, exactly, because the standard OpenMP programmer does not really know about OpenMP flush, because the standard OpenMP programmer somehow relies on the fact that at the end of an OpenMP construct, the memory is magically flushed. However, if you want to ever read something from a remote thread within the same OpenMP construct, you need OpenMP flush, exactly the same in MPI. So think about that mode a little bit related to OpenMP flush. Really the same, pretty much the same semantics, like tiny differences. Okay, so we have a reference implementation which runs on multiple supercomputers. I don't want to spend too much time on this, but I want to give you the insights that we had while we created this reference implementation. So we have an optimized way to create windows, we have an optimized way to communicate, and we have an optimized way to synchronize. And I would just want to give you a quick rundown how we do this in the reference implementation to give you some of the concepts that we use in order to implement this as fast as possible. So if you're interested, this thing is actually available on our webpage. It is still the fastest implementation on any Cray, Arius, or Gemini interconnects. We also believe that it's forward compatible to Slingshot that will be coming out relatively soon, and it uses a bunch of optimizations that Cray will probably pick up soon and put in the default implementation. We support intra-node communication using DMAP, the distributed memory application programming interface that is provided by Cray. We use intra-node communication using XPMEM, that was also mentioned by DK, which is a kernel module where you can basically map address spaces, an address space of process A into the address space of process B. So it's quite convenient. So you can cross-map address spaces, which means you have absolutely no copy overhead. You can do true zero copy. Well, I don't like zero copy because it's still one copy. At the end, you have to copy from the source to the destination. But let's call it zero additional copy operations on the same node. So it's quite fast, as we will see. First question is, how do we create windows quickly? So what is a window? A window, as I mentioned, a window is an address space that we expose, a piece of my local address space that I expose to remote processes. How do I do this fast? Well, first of all, how do I do this in MPI 2 or in the old way? Every process allocates some memory here. For example, this guy allocates memory at the address 0111. This guy allocates memory at the address 123, and this guy allocates memory at the address 120. So they completely independently allocate this memory, and now the MPI library needs to remember for each process, if you have P processes, the offset to write to. That is not very efficient. There is a more efficient call that everybody should use. It's really it's the MPI alloc win call for allocated windows. And this means that the MPI library will pick the same base address across all processes. Will at least attempt to pick the same base address. It's not always possible, but it'll do its best. Which means we have an O of 1 memory overhead for this implementation, and obviously that's much faster than looking up large tables, okay? Quite simple. There's another mode in MPI 3, which I just tell you for performance reasons you may not want to use too often. This is the so-called dynamic windows. What are dynamic windows? Dynamic windows is a form of a more dynamic, I guess, a more flexible window where you can, in the local operation, attach and detach memory regions. So without synchronizing with a remote process, you can create and remove some of your exposed memory. All the previous calls, you have to do this collectively with all communicators, with all processes in the same communicator. Right? So this is a more flexible way, but quite slow. The communication is quite simple in this implementation. It really uses this DMAP interface that I mentioned, and it also uses some of the atomics that are implemented in this DMAP interface. So for example, there's a compare and swap non-blocking implementation here, a non-blocking atomic, and it also uses non-contiguous memory access through the MPI types library. So just to give you some performance numbers, we've just seen some. Our implementation is about 80% faster than the fastest implementation on the Cray Gemini interconnect. On Arius, this is slightly less, but we are still at about 60%. Furthermore, for that's the put case between two nodes. For the get case, we're about 20% faster. That also maintains on an Arius interconnect. So for the intra-node latency, and that is now the magic of XP-mem, just similar to what DK has seen in his experiments. So we can be up to a factor of 3x faster. We are in the single-digit nanoseconds to write to remote memory, because that is exactly what a cache line costs you. Right, so we have 2 cache misses in order to go to remote memory location, remote meaning on the same node. Okay, so in shared memory, of course, using this XP-mem mode. So quite simple, the message rate is also higher. I don't want to spend too much time to give you results. If you're really interested in all the results, you can look at the CACM article from late last year, which was a research highlight, as I mentioned before. So the atomics are also quite fast. Interestingly, MPI supports a rather large variety of different atomics. So some of them can be hardware accelerated. You see this at the very low latency down here. So we can do this in the single-digit microsecond range. However, some of them cannot be hardware accelerated, at least not on today's interconnects. This is something I will be talking about the second part of my talk. How do we actually make sure that we can hardware accelerate everything? Right, so because right now we have the limitations of what the interconnect supports. So for example, the minimum operation for integers is not supported in Cray Gemini, at least. I also believe in Cray Aries it's not. So this is why we have to implement it with a rather complex protocol that ships data back and forth and applies the minimum on the CPU and not on the network. Okay, so the fallback protocol is quite nice though, because it has a quite high bandwidth for details that I don't want to get into now. Okay, the synchronization modes, I just want to briefly summarize them. We have the scalable fence implementation. So a fence is an operation that synchronizes all processes and makes sure that all operations, all communication operations that have been issued before are in fact visible at all destination processes, and for the same reason at all origin processes. So how do we do this? This is the code for implementing MPI Win Fence. We issue a memory fence on the x86 nodes, and of course if you would have an ARM, you would just issue the correct operation that would memory fence the local nodes. So which means we complete all the local accesses within each node, and then we issue a DMAP sync. DMAP just synchronizes all the remote accesses now, because it's a remote access interface. Then we issue a standard MPI barrier, which now globally completes all the operations, because until now we did not know whether remotely everybody has called gsync wait and ASM mfence. So we may make sure that this is true by calling the MPI barrier, and then we are done. This makes us, this simple thing, just quite surprising, makes us about twice as fast as the Cray implementation of the exact same functionality. However, Cray builds on MPitch. The old MPitch version implements all of RMA using messages. Right? So this is why we are faster, because we just call these essentially 3 functions here. Okay, the post-start complete wait synchronization has two pieces. We have a set of puts which go towards the posting process, and a set of puts which come from the starting process. If you're not fully familiar with the synchronization mode, just read your emails for the next 2 minutes, because again, this is like half an hour explanation usually, but it'll be over in less than 2 minutes. So here we have to employ a rather complex matching algorithm between post and start, and a quite complex matching algorithm between complete and wait. Again, the details of this is all in the paper if you're really interested. It's a quite nice implementation, and you can also see it nearly a factor of 10 faster than what Cray has been implementing. This is the first implementation of post-start complete wait that fully uses the MPI RMA, or the one-sided features of the network card, to implement all of this. It has complex remote queue accesses and all of these fancy things that you can use RDMA for. This is the first part of my talk. I will start to complain about RDMA in a couple of minutes, because it actually limits ourselves quite a bit in what we can do. Because all we can do in RDMA is read and write remote memory. We cannot really change remote memory very efficiently, besides overwriting it, which is quite annoying. Okay, but then the last piece is the scalable lock synchronization, and this is something I don't have enough time to talk about. Again, I just want to give you this overview. That was an HPDC best paper. Basically, we have a tree-based lock implementation that supports reader-writer locks in all kinds of different configurations, and this is a large design space where we can trade off, it's actually quite interesting, we can trade off latency of readers and writers together with the throughput for readers and writers, together with the fairness for the writers. So now you pick what you want. You can run your, to quote DK again, you can run your personalized lock implementation if whether fairness is important to you or latency or throughput, right? So now you pick what you want, and of course our implementation just picks something for you, but you can easily change it if you want. Okay. So then the flush synchronization is trivial, because all that does is increment a counter at the other side. We use atomic fetch and add for this. So of course, fetch and add has a time and a memory bound of O of 1 if there are no conflicts at the site. So very, very, very simple implementation. So now let me show you, let me finish that part with some insights into performance. How does this perform at a large scale? The largest system we could find at the time, it's probably still one of the largest systems that supports that mode today, is the Blue Water system. So it has more than 20,000 compute nodes. We ran all of this at full scale. Okay, so with more than 500,000 threads, more than 500,000 MPI processes, and it actually worked. Right? There's nothing surprising here. So here we have a small scale experiment with a key value store that we only ran up to 30,000 processes. But we see FOMPI, which is our implementation of MPI3, together with Cray UPC, perform at about the same rate. So we get, with MPI, with standard MPI, the same performance as the UPC implementation. That's not surprising because we are basically using the same techniques. Right, so why would we be faster or slower? No, we are not, because it's very, very similar. You see that the messaging mode is quite slow. It's nearly a factor of 10 slower than the RMA mode. Then there is a slightly different protocol where the speed ups is a little bit more modest. It's within a factor of 2. We can also run this to 32,000 processes. This is a graph problem where all the other implementations perform pretty well as well. Then I have 2 more applications that we could look at in detail. So one is the NAS 3D FFT, which is a very well-known benchmark. It's an FFT benchmark where the only benefit we get, or the biggest benefit we get, is actually by perfectly overlapping computation and communication. How much speed up can you get from overlapping computation and communication? At most, a factor of 2. You can get at most twice as fast, because you will be either dominated by communication or by computation, or by the max of the 2. Right? So we actually see this speed up at 65,000 processes exactly 100%. Right? So we are twice as fast than the MPI implementation. And again, UPC is close to us, because UPC uses the same principles. So again, in principle, we are not that different. It's just a more standard interface, a more portable interface. So here in the Milk application, we see about a 13% speed up, because we can do the communication a bit faster. Milk runs with a very low communication overhead. That is full application speed up. Milk only has about 20% communication, so we save nearly 60% of the communication overhead of the application in this particular example. And this is now the full-scale run at 512,000 processes. So that actually works and is scalable, and you can download and use it on your machine. NERSC is using it for several experiments. Right now, actually, I think they're working on a paper, but yeah, you can try it yourself. But now the question is really, what next? Right? I told you about the past, so you may not be so excited about the past, but I'm usually more excited about the future. So there's one observation, and this observation is quite annoying. It has been hitting the data center market quite badly, because even today, the CPU core speed, like a single core, cannot keep up with the message rate coming through the NIC. So a single core cannot process the messages coming through a modern NIC. In fact, if you use your multi-core device, if you were just doing message processing, you would be using on average 60 to 70% of your cores just processing incoming messages. And now you say, well, okay, that is true for TCP/IP processing and all of these more complicated protocols. Why is RDMA not helping? Well, the problem is RDMA is helping to a certain extent. But now let's look at what RDMA is doing in detail. So if you look at this wonderful Cray machine, we have these Zebra-style machines that was apparently en vogue at some point. And what happens is here we have a local node here. So packets are coming in through the NIC, going through the PCI Express bus to some main memory. And then here we have the CPU complex. So CPU complex has registers, level 1 cache, level 2 cache, level 3 cache. I just, for your convenience, I annotated the latencies at all of these elements in the, that's a standard Broadwell or Haswell CPU, so these latencies don't change too much. But let's now look at what happens here. What happens is a network is coming in from our Zebra, it goes into the RDMA NIC. Of course, the RDMA NIC has an RDMA processing unit, which basically looks at the packet. Is it a valid packet or not? If it is a valid packet, then it just scrapes off the address and figures out, does a virtual to physical translation, and figures out the location to deposit it into main memory. Right? That's what your NIC does. Your NIC is quite advanced, but still quite silly. Because all it does this address translation and puts it into your main memory. And then, of course, once you have received some data, what do you have to do with the data as a receiver? Well, you have to look at it. Because if you don't ever look at it, then you don't need to receive it. You don't need to send it in the first place. Which means you will need to take that data, load it through your memory hierarchy into your registers, process it into your registers, and then maybe write it back or discard it or add it to some other value or do whatever with it. But the key is you have to load that data, okay? The receiver has to look at that data. But let's now look at what the RDMA NIC, because it is so fast, can do to your CPU. The RDMA NIC, today if you look at Mellanox Connect X5, will give you 1 packet every 5 nanoseconds, okay? Well, look at these latencies. You will be getting a new packet every 5 nanoseconds. Of course, we all understand the queuing theory difference between latency and bandwidth. So the bandwidth is probably okay, right? But the latency is problematic here. If you just look at the PCI Express bus, right, 250 nanoseconds, but we get 1 packet every 5 nanoseconds. If you look in the future, 400G NIC, which are very soon showing up, we get 1 packet basically every nanosecond. So how the heck should the poor CPU work with this, right? The CPU has 1 nanosecond to look at the packet, read it and write it back, and do whatever processing it's supposed to do. Well, that doesn't sound great, because if you look at these latencies here, you know, that may be a problem. And especially if you have a packet processing CPU that has to load through all these caches. And if you look at what packet processing typically is, you have no reuse whatsoever. You read your packet once, you merge it into something different, and you will never want to look at that packet again, because you've already merged it. So the cache hierarchy is widely ineffective for packet processing, and including MPI processing. Because when we receive a message, we're usually reading it once, do something with it, and merge it into our data, into our local data. If you look at the Halo exchange or something like this, you will never look at this data again. Yes, you have a question? No, the difference here is between latency and bandwidth. You will not hit this as a bottleneck. It will be delayed for 250 nanoseconds, but there will be many, many, many messages in flight. That's the thing. You don't have to wait. Yeah, it is, but it's 250 is measured. Like, this thing doesn't get faster, right? But there will be many, many messages in a long queue that travel slowly through the network, but with a pretty high bandwidth. Right? They're not moving very fast. They're moving super slow, but they're wide. This is gigabyte per second, and I didn't put the gigabyte per second here, but this matches approximately. So the gigabyte per second, the bandwidth I can sustain, is just the latency that is super annoying. And the same for this memory hierarchy. I can sustain the bandwidth if I keep my core busy, many cores busy, not just one. But again, it seems like a waste here. But why don't we look at the RDMA NIC? This is a device that has been tuned for that message rate. Like, all that thing does is receive a packet every couple of nanoseconds and process it as fast as it can and move it into my main memory. Why don't we see if we can do some processing, some lightweight processing of the message in the NIC? For example, if we just want to receive a packet that does some simple accumulation, like if you look at machine learning, we've heard it yesterday. If you just look at that, all you need to do is to add the content of the frickin' packet to some other buffer. Like, why can the NIC not do this? Right? Why do I need to load this through my memory hierarchy up and down and forth and back? So the NIC could totally do the single operation per byte. No reuse whatsoever. Okay, so this is just one example, and this is something that we want to push, because today, in fact, some NICs can already do this. Some NICs can do a very limited functionality that is pre-specified for you, and that's a bit of the problem, for certain tasks. Of course, deep learning is big enough that a NIC vendor like NVIDIA, I apologize, that a NIC vendor like NVIDIA would basically get this functionality into the NIC, right? Because it's worth it. It's a $1 billion market. But HPC may not necessarily be that big of a market, and maybe some things should be more flexible than they are today. This is exactly what I want to talk about now. How do we democratize the NIC as an accelerator? So how do we see the network card itself as an accelerator device that we can program explicitly? So let me first start with some established principles for compute acceleration, because after the success of NVIDIA, now it even swallowed the NIC market, we can somewhat understand, or we should understand, what led to this success. Because remember, NVIDIA got big by accelerating certain compute workloads. Maybe we can now look at accelerating NIC workloads. But let's first see what the principles of compute acceleration are. We have specialization, obviously. It has to be reasonably easy to use. Okay, we can now argue about this. Is CUDA easy to use or not? I would argue CUDA is quite easy to use, actually, compared to many other languages that have been there before. Right, I have programmed in shader languages. You don't want to do this. CUDA is a very nice abstraction. It has to be programmable in the sense that you can write serious software engineering projects, you can call libraries and things like that. CUDA offers all of that. It has to be portable. CUDA is reasonably portable among NVIDIA devices. It has to be efficient. Of course, it is efficient as well as to support libraries, as I mentioned. And then we have several different interfaces. I should have OpenMP5 here, because OpenMP5 is really the better way to program accelerators. Better than OpenMP4, okay? So we should really look at these principles, and now the question is, can we do this in the network? The answer is yes, we are working on it. The idea is to develop an offloading framework to network interfaces. And I now want to use my last couple of minutes to explain you a little bit more how this could look like. How do we democratize NIC acceleration in a similar way that we democratized compute acceleration? So we kind of need an accelerator language, an accelerator system, and an accelerator idea. So first, every reasonable language has an abstract machine model. So how does the abstract machine look like? We all know how compute abstract machines look like, because they have a processor, they have some memory abstraction, some registers, so that I don't need to explain. But a NIC is slightly different. The NIC abstract machine actually has definitely an input memory for packets, right? Because a NIC is a packet processor. It must store packets somewhere. It must have a packet scheduler that takes arriving packets. So this is my transceiver here. Here come the 400 gigabit per second data stream that the scheduler chops into packets and then assigns to my input memory. And the NIC has processing units. This is actually what the Mellanox NIC or any RDMA NIC has today. They have processing units. They're partially programmed in silicon. They're partially programmed in firmware. So they have already all of these pieces on it. Then the NIC has to have a DMA unit, because at the end, the NIC needs to DMA that data into main memory. So this is a DMA unit, performs read and write to memory. And what we also have in the abstract machine model is, of course, our CPU. But now the CPU up here doesn't do any packet processing, because all it does is similar to what the CPU does on a GPU. What does the CPU do on a GPU? Well, it installs code on the GPU, and it executes code, or it starts the execution on the GPU and manages memory on the GPU. But it's not doing much else. It's not performing much computation if you fully offload your memory or your computation. Here it's very similar. So the CPU uploads handlers to the GPU, to the network card, and the network card executes these handlers on the packet. And of course, there needs to be some memory management, which is also done by the CPU. So in this sense, the network card does not run an operating system. Similarly to an NVIDIA GPU today, or any GPU today, we do not run an operating system on the accelerator. We may do that tomorrow, but at least not today. It's fully remote managed by some other entity that is the CPU. So what happens then in the processing path? Well, all these packets come in, they go into this memory through the packet scheduler, and then these packets are scheduled to the processing devices. By the way, H means handler, because we upload handlers. So each packet is now processed by the handler processing unit of its choice. There are usually hundreds of those in a modern NIC. And then it's going through the DMA unit, changed, right? It changed shape here into the main memory. And now the CPU may not even need to do anything with this packet. It may already have been fully processed by the NIC. The common case will, of course, be that the CPU still does something and the NIC does only pre-processing. And I will give you some use cases for this model. So to go a little bit more into detail, let me explain you how it works from a messaging perspective. So we have the CPU here, CPU and memory. We have the NIC here. That's the origin or initiator. We have the CPU, the NIC at the destination here, and the CPU and memory at the destination. What happens in RDMA? Well, the initiator sends or instructs the NIC to send a piece of data. It'll send it to the remote NIC. The remote NIC will commit it to main memory at the target, as we've just seen. And then in a ping pong benchmark, the remote NIC will just send it back to the origin, will send it back to the NIC, of course, and is going to be, the same message is going to be deposited into memory at the initiator. If we now look at the SPIN programming model, so this offloading programming model, we could do the following in a ping pong. We would still initiate the data from the source. It would hit the target NIC, but instead of committing to main memory at the target, which we have to do today, okay? Remember, we have to do it. Even with accelerated NICs, like Portals 4 NICs, the data is still going into the main memory. On a SPIN NIC, because it's packet by packet, we could forward this to immediately back to the initiator without having the packet hitting the main memory. Okay, that is the difference. It's also the difference to Mellanox technology today. We can do this fully on the NIC. It doesn't need to ever hit main memory. Now the power you only see if you look at multiple packets. So here I'm just showing you 3, because what's happening in RDMA, we have 3 packets pipelining through the network. And only once all these 3 packets hit the destination memory, the reply message can be initiated. Right, that's quite important. Only the full message arrives, we can start the reply. And now if we look at SPIN, which is a packet by packet forwarding layer, we can actually forward these packets, and this is much of the Kool-Aid, before another packet even arrived. Right? So packet by packet, we will just process and forward these packets. And this is much of the conceptual benefit over active messages and over NIC acceleration we have today implemented in many NICs. Okay, so just to elaborate a little bit more on the programming interface, as I mentioned, it's a packet-by-packet programming interface, so it has to be slightly more complex than a messaging interface, because we don't wait for the full message. We have to tell the NIC what to do with every single packet now. Which means, if you look at a message has multiple different types of packets. It has a header packet, which is usually the first one, right, which identifies where the packet should, or where the data should go. It has several payload packets, and it may have a last packet, which is the tail packet. So through the packet scheduler, we now schedule these different packet types to different handler types. So you specify as a programmer, or the programmer specifies a handler that handles the header of a message. The programmer also specifies a second handler that handles each of the payload packets. And the programmer specifies a last handler which is invoked after all payload packets have been processed. So with these 3 different handlers, so these are essentially the same as CUDA kernels. Like you download each of these handlers to the NIC, tell the NIC for what message you want this handler to be invoked, and there's the interface on the bottom. You can just attach this to your connection. And the NIC will then execute these handlers on every single incoming packet, respectively, for each message. Okay? And this is massively parallel. You have to now imagine that they're running, the NIC is running hundreds of copies of this at the same time, because you always have hundreds of messages, maybe even thousands in the NIC at a given time. Okay, that's the programming model. We can easily implement this with a very large number of NICs. In fact, I'm claiming you can implement this today with a firmware change on most existing NICs if we had access to the firmware. Right? So of course we don't, but this is exactly why we want to go through this democratization. If you talk to network experts or network designers or architects, they will tell you the only thing you never do in a NIC, like the place you will never touch, is obstructing line rate. Because if you sell a 400G NIC or a 200G NIC, and the NIC does not do 200G, then I heard Sadaf will call you. Right? Because that's the problem. You need to deliver what you sell. And which means it's extremely hard, because at 400G you have to process 833 million messages per second. That's quite challenging. CPU cannot do this, but a specialized NIC can do it. So we did the calculation. We have a simulated implementation. We in fact have now an implementation on an FPGA together with a collaborator, Luca Benini. And this all works. We can do this on multiple NICs. We have an implementation on a Linux-based Broadcom NIC today available. We are working with multiple companies to actually make this happen, and we have a full simulation framework, as we will see in a couple of minutes. So we opted for simulation because you can actually download, if you're a NIC vendor and interested in this, you can download our simulation toolkit and just repeat all these simulations for your particular setting. Right? If you want to check your NIC, you just plug in your NIC's parameters and you can see if that would work for your NIC. Here we have just some parameters we chose, not randomly, but this is basically a 400G, an envisioned 400G Mellanox NIC. Right? So if this would exist, then this would be the NIC to go. And for the processing, we use a 2.5 gigahertz ARM Cortex device. So it's just a standard ARM CPU that you can buy off the shelf, integrated into the NIC. In fact, this is quite close to what the Broadcom NIC is. So the Broadcom NIC, the Broadcom SoC, has an 8-core ARM, pretty beefy ARM CPU on the NIC that you can program quite freely. So it's very similar to that guy here. Okay, just to show you again some simulation numbers. If you now look at the half round trip time, so this really latency here for RDMA, and again remember this is this optimized RDMA that I showed you, optimized for SPIN. We do get a lower latency, 35% lower latency on this setting and 32% higher bandwidth, and this is the streaming mode that I mentioned. What's even more important is that the number of instructions per packet to execute on the CPU is quite low. So we have to issue only 18 instructions to process a single packet. And of course, we cannot afford more than a couple of hundred instructions anyway, otherwise we don't get 833 million messages per second. Right? So that's quite clear. These handlers, they must be very cheap. So now I want to give you 3 use cases very briefly that we can also use for network, or that can benefit from network acceleration. The first one is broadcast acceleration. If you don't like broadcast because you're a machine learning person, if you like reduce much more, even all reduce, it's basically the same thing for all reduce, just more messages. So just bear with me. What does a broadcast do? You probably know. A broadcast sense has 8 nodes here. Again, we draw the CPUs and the NIC, the memory and the NIC separately for these 8 nodes. And we have a single packet at the beginning. What we want to do is we want to distribute that packet as fast as possible to all these 8 nodes. How do we do this in RDMA? Well, we instruct the NIC to send this packet to our friend, node number 2. It'll go to main memory there. And again, the CPU instructs, the 2 CPUs now instruct the NIC to forward this. And then again, the 4 CPUs now instruct the NIC to forward this. Remember, in RDMA, the CPU will instruct the NIC. Because that's what RDMA is. RDMA, you can only send data or put data in remote memory. So this is the latency we get. And now we could argue, okay, well, we know how to do this better. We will hear about SHARP soon. So how would we do this in an accelerated network interface? We would do the same thing, but not the CPU would do it, but the NIC would do it. SHARP goes one step further because there the network even collaborates with you. Like the switch in the network will help you perform the operation. Here this is just NIC acceleration. But the idea is that we now don't have the CPU initiate the transfer, but the NIC initiates the transfer, yet the packet is still residing in main memory. The reason is very simple, because I could be broadcasting a 1 gigabyte message and the NIC doesn't have 1 gigabyte memory. Right? So I need a packet level interface, because with SPIN I can broadcast a 1 gigabyte message because I will process each packet. And the packet is a very small size, right? Otherwise it wouldn't work. Okay. And then you do the same thing here. Then you look at the performance. This is basically what an offloaded collective gives you. So the older Connect X2 would be that, for example. But now if we do it with SPIN, and now you can get the idea, we don't ever commit the packet into, oh no, actually we do, because eventually it has to end up in main memory. But we don't do this before forwarding. We forward the packet before we commit it into main memory. And this is why it's substantially faster, because we don't go through this 250 nanosecond PCI Express bus. This is the big difference here. And then you get much faster. The nice piece is that we, again, only need 24 instruction plus log P puts. In this case, it's a binary tree. The binary tree has 2 puts, right? So quite small. Then you could even implement a more complicated protocol, which is, in my view, quite nice, because you can implement a full distributed database or a distributed file system on the NIC. Right? Imagine you want a distributed RAID system. Why would you even involve the CPU? In a RAID system, the computation is trivial. It's just applying a freaking hash function, which is very often an XOR. Right? All you do to your packets is XORing it. I mean, the NIC can totally do XOR for you. Right? So this is a very, very simple concept. Here, if you do this with RDMA, what you would do, if you receive a write, And then, oh, by the way, this is a server node that processes your writes, and then we have a parity node, because let's assume we are Amazon. We don't want to lose our credit card transactions, so before telling the writer that the credit card transaction succeeded, we will actually make sure it's copied to a different node, right? That's what we call a parity node. And then what this server node does, it receives it by this in its main memory. The CPU in the RDMA case triggers an update to the parity node. The parity node processes the update on the main CPU, because again, RDMA can't do it, and then sends the acknowledgement back, which again goes to the main CPU at the source node, and only then the writer knows. So that's your latency. You would get about 3 microseconds, so that's actually quite fast, right? But if you do this with SPIN, oh, I apologize, the animation was too fast. If you do this with SPIN, what you would do is you would do the processing on the NIC, you would not involve the CPU, and the parity update would basically be sent from the NIC to the remote NIC, where the remote NIC just updates the memory. Right? So there's no involvement of the CPU, because, I mean, this freaking XOR update function, any NIC can do. This is a single cycle operation in most reasonable hardware implementations. Okay, so this is much faster, and you see here 20% lower latency, but nearly twice the bandwidth at the end. Okay, and much cheaper, of course, because now I don't need the CPU anymore. I can use the CPU for something else. So this is kind of what I mean by network acceleration next generation. RDMA takes parts of the load of packet processing off our CPU, but SPIN will take a bigger part of the CPU. Right? So, and then you can program the NIC yourself. Okay, the last example I want to move a little bit faster, which is data type acceleration. We've heard much about this in the previous talk. And the idea here is that, again, in RDMA, what you do is you send the data, as you've just seen, through the NIC into the main memory. Then the CPU reads it, and then copies it into the actual destination memory with a strided access and whatnot, so with a different structure. But of course, obviously now what you could imagine, I mean, this is the bandwidth you get, and what you can imagine is you can now, well, just let the NIC do exactly that, because all it does, it splits up the messages into smaller accesses and then writes those accesses into main memory. And again, this will get you a very high speed up in the best case. So it's actually harder to get, this 4x speed up is quite positive. So it's harder to get this in practice. In practice, we see more like a 2x on average across a very large set of data types. So we have many, many different use cases. We can also accelerate the rendezvous protocol. I haven't talked about this. It gets much faster for communication. We can actually implement a full distributed key value store on the NIC, right? Because a key value store is quite simple. You just implement this on the NIC. 41% lower latency. You can have conditional reads to accelerate distributed databases like distributed MySQL, for example. We can have distributed transactions, which is quite nice. If you now think about memory, transactional memory, we can implement transactional networking, right, using SPIN. You can implement a fault-tolerant broadcast. At the end, fully process everything on the NIC. And you can have even a distributed consensus protocol, which is then the holy grail of data center networking, where the consensus fully runs on your distributed set of networks. The next 700 use cases are going to be graph algorithms. I'm sure there will be at least 700 papers on how to do graph algorithms in that model. So with that, I would like to conclude my talk with a quick overview. One more thing, again, we want to support more complex network interfaces, acceleration for the masses. We collaborate with Luca Benini. We have a RISC-V SoC that can actually go on the NIC with a specialized memory hierarchy that we can install today on an FPGA. Okay, it's not on a NIC, but we try to push this towards vendors to also democratize that market more, because all you need is you need to put up a transceiver in front of that SoC, and then you can do most of this. We work in deep learning quite a bit. I haven't talked about this. Be careful when you look at deep learning results, at any deep learning results, so this is just some warning. And then the last thing is we're having a conference in Switzerland again, if you want to come back, in September in Zurich. That's Euro MPI, and I want to invite you to this in case you're interested, and thank you very much, and I'm open for questions.